Hello, YouTube viewers. I, Anupam Vipul, is welcome you to our interview with one of the world leading scientists who is working in the technology of capacitors, battery, and energy storage. So, Mr. Rajendra Sharma, can you give us your introduction?
Yeah, basically, we are into capacitors, supercapacitors, and energy storage product. And I'm in this field since 1986. Since 1986, we are into manufacturing of capacitor. And later on in 2012, we developed supercapacitor. After that, the enhanced versions of those supercapacitors were developed. Like the first version, activated carbon supercapacitor.
Mhm.
The second one, lithium-ion capacitor. The third one, hybrid. And we have a unit in Pune. It is India's first supercapacitor manufacturing unit. Apart from that, we are industry partner to Ministry of Electronics and Information Technology for the Center of Excellence for Lithium-ion and Sodium-ion battery, wherein we are giving technology for lithium-ion and sodium-ion battery to small industries to build up a manufacturing ecosystem at MSME level. So apart from that, we are also working on quantum supercapacitors. In fact, we have demonstrated that. And also we have developed solid electrolytes. So very soon commercially we'll be making solid state battery also available to India.
Okay. So, just to clarify why we are working with Ahiravata is simply because Ahiravata is an engine manufacturer. Now, no matter
Right.
which engine you are dealing with, engines generally like to stay on efficiency island where they will give you the best conversion efficiency. We generally measure it using brake specific fuel consumption. It removes the engine size and all variables. And basically, if you buy from, let's say, Toyota or any other manufacturer, the best you can get is 200 grams per unit of electricity. That's the best conversion efficiency. If you are buying a quality 4-stroke diesel, you can get it down to 180 grams of fuel consumed for 1 unit of electricity. Now, here's the deal. If our engines are so efficient, why we are not getting such a very high mileage in real world use condition? Well, problem is engines like to stay at that sweet spot. That sweet spot requires two vectors to be controlled. First, it's RPM. It cannot be higher nor it can be lower. And it's torque loading. It cannot be under low torque or it cannot be under high torque, overloading basically. So that sweet spot is not maintainable if you are directly coupling engine to the wheels, because road condition are variable. You could have wind loading, you could have gradation, you could have lower air pressure. All these things make it variable. So your engine control computer with your accelerator input tries to do its best. Penalty of it is that it's never as efficient as it theoretically can be. To solve this, the best technology we have is what we call a series hybrid, meaning combustion engine just act as a base load generator. It does not do anything other than it just starts, ramps up to the sweet spot, stays there, the end. It does not do anything. But how do you run the system? Well, again, we need energy storage to make this viable. All the base load power, let's just say 100 kilowatt, goes into your tank. Then this energy storage tank gives it to your motor. Now, again, let's say you are rolling down a flyover, you do not need that much energy. So a tank starts to fill up a little bit more because, again, motor is not consuming a lot. But let's say you are trying to take over something, you need a lot of oomph, maybe more than 100 kilowatt, which is quite easy to do. But this time, instead of asking energy from generator, it asks from the energy storage. That way we can isolate the engine, and that's the easiest way to give the most energy efficient possible. There is no other technology that allows us to do that, but penalty of that is you must have a good energy storage. So to solve this dilemma, how the heck we can, because we can solve the engine part, but if we cannot solve energy efficient part of energy storage, it's spinning in circles. So we are directly working with Rajendra Sharma to create a tool that allows us to properly solve this issue without having issues. So Rajendra Sharma, would you clarify what are the limitations that you have faced when you are dealing with lithium ion batteries in this sort of application,
Yeah.
basically focusing on high current?
See, basically in case of Ahiravata or any other hybrid vehicle, wherein it is expected the harvested energy should be stored in certain storage device. and given back when it is required. So basically what you require expect from that storage device, it should have an ability to absorb that energy or harvest that energy immediately as available. That is one requirement. Second requirement, it should have enough space, because the vehicle condition, the brake application, it is not in our hand. Sometime you may require more space. So adequate, decent space should be available. Whatever energy is generated, it should be captured immediately, and there should be additional space left. So in electricity or any energy storage device, there are two functions defined. One, when we talk about the capability of device to absorb the energy immediately or get it charged immediately, is related to the power density capability of the energy storage device. And the space required is energy density. The units are different. Energy density is measured in watt hour per kilogram, and power density is measured in watt per kilogram. Now, I've seen many people, I don't want to name it, they are claiming they have regenerative energy capturing arrangement. Now, how that arrangement is done, the energy is captured and stored into battery. But in battery, you must have noticed there is a C rating of the battery. Or normally the battery comes in ampere hour. Okay. And the lithium-ion batteries are generally, you can take it as 1C. So in any vehicle, if you have a power pack, for example, you can take an auto rickshaw or maybe a car. Depending on the wattage, the ampere will be maybe suppose 40 watt hour, or maybe depending on the size. So what it means, whatever is mentioned on the battery, that is the maximum current which can respectfully induce into the battery for charging. But if you look at the regenerative energy, a vehicle weighing around maybe 900 kg, and if you are applying the brake, and like your speed is suppose 60, stopping in 10 meters, during that time, roughly 900 ampere is generated, around 800 to 900. That kind of intake capability is not available with the lithium battery at the basic level. That is one part, but the major part is that if you have a lithium battery or any other battery installed in your vehicle, remember one thing, batteries cannot be charged while it is being discharged. So if it is an electric vehicle, you are running the vehicle on electric. So it is a eyewash to say we have a regenerative energy capturing arrangement unless and until you have made a separate compartment, a isolated battery system for that. Okay. Now coming on to this bottleneck, this can be easily taken care of by supercapacitor. They have the capability of very high power density. Battery doesn't have that capability. Of course, battery do have the capability of energy storage, that is watt hour per kg, that is related to your backup. But so far power density is concerned, they lag into that. If numbers are to be believed, typical example, lithium-ion battery, around 200 watt per kg. As in comparison to that, supercapacitor is 10 kilowatt per kg. It is 50 times higher. But energy density in supercapacitor is less. Again, how much less? Maybe 1/5 or 1/3, as low as that. So that is, I'm talking about the first generation supercapacitor, or to be more specifically, the generally commercially available supercapacitors, activated carbon supercapacitors, whose energy density will be around 6 watt hour per kg. With 6 watt-hour per kg, you cannot bank on much if you are targeting energy density power. Okay, power density, of course, 10 kilowatt or so, 8 to 10 kilowatt. Now, if you want to optimize the system and make a best use, a general acceptance will be the customer will be expecting they want an energy storage device with a decent energy density and a good power density capability. Now, how this can be achieved? Basically, commercially, you don't get above 11 watt hour per kg, best of the best case, which is in activated carbon, or those 11 watt is around curved graphene or something like that. That kind of technology. So, what we did, we developed lithium-ion capacitor. That is a supercapacitor. In that process, the energy density got enhanced by over 3 times. In this, what we have done in lithium-ion capacitor, it is a capacitor. The anode and because activated carbon capacitor, anode and cathode is same, both the side carbon. In this case, one side was carbon, other side is hard carbon. And of course, lithium electrolyte, LiPF6, and pre-lithiation was done. The energy density what we got is 23 watt-hour per kg. Now, we didn't stop over there. Then we made a hybrid version of lithium-ion capacitor and battery. Why that was required? Because if you look at especially electric mobility, they want both energy density and power density combined. So what people have done, some manufacturer, it is a general, what you call it as a approach. What people do, they combine battery and supercapacitor externally. They take battery separately, they take supercapacitors separately, put them together in parallel with electronic interface. The idea is to get best of both the world. But in this process, what happens? The worst also gets combined. What is the worst? In supercapacitor, okay, what is the worst?
Sir,
Worst is they don't have energy density. Okay, means not to that extent. The rest of the things are absolutely fine. But as expected by customer, the collective hybrid power pack is not able to charge fast. That is the bottleneck, because the maximum charging time will be governed by battery. So what we did, we combined the things internally. We made a composite cathode material of activated carbon and lithium battery active material, put them together in a definite proportion to optimize in such a way all the properties of supercapacitors are retained. Mostly the desired properties, like fast charging, low self-discharge. Of course, low self-discharge was not the phenomena in the generation 1 supercapacitor. It started in generation 2 and generation 3, means lithium-ion supercapacitor and hybrid version. So safety, major is safety. Okay. So we have a hybrid supercapacitor whose energy density we were able to reach 65 watt-hour per kg, over 10 times the initial value. And the power density, of course, there was a slight decrease in power density was noticed, and it is around 5 kilowatt per kg. But any mobility or electric vehicle, they don't require above 2 kilowatt per kg. So that is pretty excellent so far automobile industry is concerned. So
Okay,
that is the brief idea of that, and the same thing we are using it in Ahiravata.
Okay, so let me summarize what I understood so far is that battery and capacitor they basically master two different domain. Batteries are very good in kilowatt hour, basically how many unit of electricity you can store on that. Batteries are very good
Right.
in that. But when you compare it to capacitor, supercapacitor, whatever have you, they are very good in power. Basically, how many joules it can dump quickly. There is no competition. Basically, you are limited by the resistance of the material rather than the chemistry. It's very good. However, while it has the power, the oomph that is needed, it does not have the tank capacity. Basically, if you make your whole car out of supercapacitor, the kilowatt hour capacity will go down drastically. So let's say Tata Nexon, I think, has 75 kilowatt hour. If we do with supercapacitor, we'll have more than enough power. It can even run 500 horsepower electric motor without any issue.
Right.
It's just that it will not have the range, basically, because the unit count would be so low that is like we start, we go and done, so battery done. So, and both of them have pros and cons like this. Basically, capacitor, because again, it's storing energy, to put it roughly, in electrical fields, and battery is putting energy in chemical reactions. It is very slow. Fundamentally, capacitor can charge at very high C rating. I mean, like its C rating will be pointless to describe on capacitor, is so fast. Batteries 1C, and yes, on paper you can put a lithium chemistry higher than 1C, but problem is it starts to overheat. So you may require cooling systems, or you may require battery to be at specific load for specific state of charge. Basically, if it's a 20% what you call state of charge, then you can increase it, but only for short duration. That's why no matter which mobile phone you buy, fast charging only takes you from 0 to 80%. It will never take you from 0 to 100. If you do that, it will cause damage. So that's why basically we have two things. One has the power, more than enough power than we need, but does not have the capacity. Batteries, it has more than enough capacity, but does not have the power. Many times we have to make larger battery just so we can match the power rating. And basically, when we are accelerating, generally we can decelerate faster than we are accelerating in civilian cars. So you are creating a lot of oomph, lot of amps, and lot of kilowatt that is trying to be recuperated. Now, trains also have the same issue, but they generally dump the energy into resistor vac, which we call dynamic braking. And modern electric locomotive can even do regenerative. But here's the deal, that is so much energy that you have to do something productive with it. Right now, in normal car, we just waste it as a heat in our braking system, but in regeneration we want to utilize it properly. But here's the problem, motors can easily convert into basically going from motor topology to generator topology. That's sorted. Our motor driver can easily extract energy. That is sorted. It's just the moment we touch batteries, that becomes the bottleneck, not the rotational part. It's just the battery cannot absorb energy fast enough. And if it's not fully drained, let's say battery is a high state of charge, let's say 90%, it will just reject it. At that point, your computer will detect it's like, hey, battery is fully charged. Let's use the calipers, disc brake calipers or drum brakes to slow it down. So capacitor, in those sort of scenario, it does not care. It's like, bro, it's like I'm 0% state of charge, 8% state of charge, or 80% state of charge. It can handle that surge. So your technology specifically allows us to merge these two competing requirements, the capacity and the power surge that we need. So can you dive a bit deeper, just again for a layman person? It's like
supercapacitor and battery, fundamentally, you rightly said, they are two distinct technologies, fundamentally. But practically, they are complementing technology.
Okay, can you just dive deeper into like what's the core difference so everybody can understand what we are talking about? What do we mean when we say capacitor? What do we mean when we say battery?
Basically, fundamentally, the energy storage mechanism which is used in supercapacitor is non-Faraday. That means the energy is stored on the surface area. There is no conversion. Means electricity is stored in original form. So when you are storing something in its original form, you can store it very fast because conversion is not required. Whereas in battery, the storage mechanism is Faraday, wherein the input electric energy is converted to chemical, stored, and kept for usage, while using again reconversion. So the conversion, reconversion, of course, losses are there. So the efficiency factor comes into the picture. But in supercapacitor, that is not there. Okay. And these two are two fundamental difference between them. That is why this non-Faradic mechanism allows supercapacitor to absorb the energy fast or to get it charged fast and deliver it on demand, how much as required. And because of the Faradic mechanism, batteries technically can't do that. Even if somebody claims fast charging, of course, that is a jugglery, what you call it. Because the electronics, you are continuously monitoring the temperature, trying to see what is happening if I'm pumping fast. That kind of thing is there. But that is under distressed condition, fast charge. If it is regular, of course, in one charge also, it creates an adverse effect to a certain extent of the battery. And regular thing will reduce the life of battery and risk is there. Now, when we talk about this electric mobility part, you said, suppose a manufacturer is giving an electric car, claiming the range, for example, 100, in one charge 100 kilometers. That they are solely relying on the battery for that. Okay. So battery, because remember it is an automobile, in olden days or even now, you have a first gear. In first gear, what is there? Power density is there. But can you get mileage out of that? No. If you are running your vehicle in first gear, you will not get mileage. In the last gear, power is not there, but mileage is there. So what is happening in electric mobility? The battery has to perform duty of first gear as well as fourth gear. So when the OEM manufacturer says, in one charge the vehicle can go 100 kilometers, it will not go 100 kilometers because the road conditions are dynamic and the power density requirement has not been accounted. So to get a practical mileage, straight away minus less 30% at least from the claimed mileage. But if you are using supercapacitor along with the existing battery, then the best people will do their work. Like whenever power density is required, supercapacitor will support that. Whenever energy density is required, battery will support that. And this system will give you a better mileage and it will act like a range extender also, which already Tesla's model has done that. Okay. So, and if you want a better user experience like pickup, supercapacitors are the best thing, because if you are trying to use battery for higher power, it will do that forcefully, but at the cost of the mileage, final what you have to say.
Okay, so when we are talking about this sort of in-depth, I would like to understand when we are talking about life cycle, basically how many charge and discharge it can handle. Why is that when battery on paper, it's a solid state device. There is nothing, we do not put liquid into it or extract liquid out of it. It's like a lithium-ion is a sealed system and capacitor is also a sealed system. So why is that capacitor can work for 30, 40 years or maybe even longer, especially if it's not overheating, and battery will like literally you have to count its cycle, basically 3000 cycle, 5000 cycle. So why is that a difference?
Say, basically chemical reactions are involved into that. Okay. Reduction oxidation is involved. And interconnection system is there. In a lithium battery, you are inserting ions and pulling it out. Okay. So normally, like if you take a case of lead acid, the cycle life is around 300 cycles. In lithium-ion battery, there are n number of chemistries, maybe LCO, LTO, LFP, lithium-ion phosphate. So practically, the most popular battery is a lithium iron phosphate for your electric mobility. Of course, nowadays, nickel, magnesium, cobalt is also used. In case of LFP, that is lithium iron phosphate, the cycle life is around 2000. In case of NMC, it is 1500. Whereas in supercapacitor, it is anything about 2 lakh.
200,000.
Yeah, 200,000.
Mm.
There is a huge difference.
Mhm.
And depending on your usability, you can count. So you rightly said, very 30 years, 40 years. Okay. But definitely in automobile, the life which is defined by RTO
Hmm.
is 15 years.
Mhm.
So it can last 15 years lifetime.
Basically, other components of your vehicle will go bad before the energy storage is the weak
Energy
becomes the weak,
storage.
weak link.
Yeah.
So okay, so what challenges do you face when you try to mix these two basically almost opposite technologies? One has the capacity, one has the power. So what were the challenges that you are facing to mix these together?
Say, even though they are opposite technology,
Mhm.
they are converging technology.
Mhm.
Okay.
Mhm.
Converging in the sense, if you list out pros and cons of
Mhm.
battery and supercapacitor,
Mhm.
battery needs to improve
Mhm.
energy density.
Mhm.
Whereas, supercapacitor needs to
Yeah.
improve energy density,
Mhm.
whereas battery needs to improve power density,
Mhm.
safety part,
Mhm.
and the other aspect.
Mhm.
So, whatever development is happening
Mhm.
in the domain of supercapacitor, in the domain of battery,
Mhm.
batteries want to behave more like supercapacitors.
Mhm.
Supercapacitors want to behave more like battery.
Mhm.
Technology wise, they are almost at saturation level.
Mhm.
So you need to borrow the things from each other. Okay. So in India, we have a very good technology, Jugaad.
Yep.
Yeah, that is respectfully known as hybrid in
Yep.
case of component combining.
Uh-huh.
And in chemistry, it is known as composite.
Mhm.
Composite is nothing but hybrid,
Mhm.
or in our language, Indian language, Jugaad.
Mhm.
So if you take a active material of lithium battery,
Mhm.
it is cathode,
Mhm.
wherein the lithium compound is actually placed in cathode.
Mhm.
So a proper chemistry composition
Mhm.
of activated carbon, which is a carbon,
Mhm.
and mixing of lithium active material put together, wherein you induce a mechanism of ferritic and non-ferritic
Mhm.
at the cathode and acceptance at the anode. Your anode should be capable of uh, doing intercalation activity and also surface storage. So normally in lithium battery, the anode is made out of graphite.
Mhm.
Graphite is good what you facilitator for intercalation,
Mhm.
but it lags in surface storage. So we are using hard carbon, which will support.
Sorry, art carbon?
No, hard carbon.
Hard carbon. Okay, okay, okay.
Yeah, hard carbon.
Do you mean like a diamond powder kind of thing?
No, it is made from the waste or algae, basically.
Okay, okay,
Yeah.
okay. Okay, so we have talked about the lifespan and the mechanism. Now, explain about safety. Which has better safety, and how do you deal with the flammability of lithium?
See, flammability of lithium, the major cause of the flammability is the oxide level or oxide compound.
Mhm.
The cathode, I told you, it is a lithium oxide. If it is lithium iron phosphate,
Mhm.
it will be a lithium iron oxide
Mhm.
or lithium cobalt. This oxide of lithium metal.
Mhm.
So imagine in your battery you have three components:
Mhm.
anode, cathode, separator.
Mhm.
These are three immersed in the electrolyte.
Mhm.
Suppose in case of abuse or some fault,
Mhm.
what will happen? There will be a arcing between anode and cathode. They might get internally short. Why it is? Arcing is there. In arcing, what will happen? The lithium metal oxide will burn,
Mhm.
will react,
Mhm.
and it will release oxygen.
Okay.
Yeah, and oxygen will support
Further combustion.
further combustion. It is as simple as that. And the electrolyte is highly volatile.
Mhm.
आग में घी डालने का काम होगा.
Yeah. So that's
So
why
that
it's so
is
hard to put out, because it's generating its own oxygen. It's
generating
self-sustaining
correct.
fire. Basically, it's a self-sustaining
Yeah,
fire.
self-sustaining fire. Now coming on to supercapacitor,
Mhm.
there is no oxygen compound in EDLC.
Mhm.
It is carbon.
Mhm.
There is no oxide into that.
Mhm.
So those first generation supercapacitors are absolutely safe. No thermal runaway. Basically, that terminology is there in battery, thermal runaway.
Mhm.
Now, when people say, "Arey, you are having lithium-ion capacitor also,
Hmm.
lithium battery,
Hmm.
वो तो आग पकड़ेगा,
Mhm.
it will catch fire."
Mhm.
But again, in lithium-ion capacitor, we are not using any oxide material. Our cathode is completely carbon.
Mhm.
Our anode is completely hard carbon.
Mhm.
Only electrolyte is LiPF6, which is a lithium compound.
Okay.
So in case of puncture or this thing, there will be arcing, of course, but there won't be any oxygen available inside
Hmm.
to support combustion. On the contrary, what we have observed, there is an endothermic reaction. The temperature goes down in lithium-ion capacitor.
So you are saying it's creating some sort of compound that is absorbing heat from the surrounding. Okay.
Surround it. The endothermic reaction takes place because of presence of carbon.
Okay, that's new.
Yeah, and the temperature goes down. It's brought under control. Basically, it is absolutely safe. Now, coming on to the hybrid version,
Mhm.
definitely you will say, okay, forget lithium-ion capacitor,
Mhm.
forget that EDLC, there is no oxide. But in your hybrid version,
Hmm.
you are using lithium oxide,
Mhm.
metal oxide.
Mhm.
So in that case, definitely there will be a release of oxygen.
Mhm.
But remember, our cathode, where is some mixture of carbon.
Mm.
That oxygen will have more affinity of getting aligned with the carbon, which is already present over there.
Okay.
Yeah. So carbon dioxide or that kind of thing is released. And in this case, what will happen in case of abuse
Hmm.
or any short circuit? The end result is not fire. The end result is release of gas.
Okay.
Yeah, in lithium-ion supercapacitor, the end result is slightly temperature goes down and small gases are released.
Hmm.
Whereas in hybrid supercapacitor, there will be release of gas, fumes,
Hmm.
not fire. So
Okay.
these are absolutely safe.
So even if it punctures or any accident happens
Yeah,
on a vehicle, it's not gonna become a fire hazard because it's not releasing
no,
free
no,
oxygen for other cells to catch fire. Basically,
catch fire, and the flames are
Hmm.
not being supported inside. The arcing is not converted to flame,
Mhm.
burning part.
Okay, but wouldn't that create a issue with like, because again you have a capacitor, you can dump so much energy, the arcing would be much higher, because again the current is no longer limited by the resistance. So when you are creating arc, it's creating a plasma which has almost negative resistance, where it's like it creates it sucks more energy, gets bigger and hotter. So wouldn't that create an issue?
No, in that case, what happens? Normally, it is a combination of power banks, is number of cells.
Hmm.
If your one cell is punctured,
Hmm.
whatever energy
Hmm.
is available into that,
Hmm.
that will be nullified inside.
Okay.
Yes, that will get discharged.
Hmm.
After that, because you are not supplying energy to that continuously.
Okay. Okay, so it's there is no electrical runaway also, because again, while not having fire, having CO2, that may be a good thing, because let's just say something else catch on fire and this starts to release CO2, that will act as a fire suppressant.
And normally what happens in the system,
Hmm.
there is a protection, fuse protection is there.
Hmm.
That particular cell gets isolated.
Mhm.
So the electrical runaway, what you have, made a new terminology
Hmm.
that is isolated because of the isolation part, means
Hmm.
fuse or cut off.
Okay. So you can basically trust this that it will not become a runaway issue for well, even long time. And
No, supercapacitors are absolutely safe. There is no thermal runaway in that, like battery.
Yes, right now we also use supercapacitor in dash cam because again that's a very hot environment inside a car when it's like supposed to be left in the sun. If people used to use lithium-ion batteries, but they did not last because it's very hot, like 60, 70 degrees Celsius. So what sort of temperature resistance your capacitor can have?
Yeah. This temperature, if you take lithium batteries, the higher temperatures, remember India is a tropical country. Even the place where we are sitting right now, the temperature is around 40. Now, all these lithium batteries, they are more focused onto the region, Western countries, wherein the ambient is around 25. Okay, like lithium iron phosphate, they are comfortable up to 35 degrees. NMC batteries, lithium ion, they are comfortable maybe up to 30 degrees. When I say comfortable, that is a maximum thing. Lithium titanium oxide batteries, they are comfortable up to around 45 degrees. So that is the comfort zone of the battery in terms of temperature. Supercapacitors, it is around 70 degrees.
Okay.
So
basically, you have much bigger problem if you are above 70 degrees Celsius. So I'm pretty sure you do not have to worry about your vehicle. If it's above 70 degrees Celsius, you do not have to worry about it.
Now the other part also counts, the lower temperature. Of course, India, very rarely we have that kind of low temperature. It is only in the Ladakh region or that. But supercapacitors, what we manufacture, we can go as low as minus 60 degrees. That is minus 60.
So won't electrolytes freeze at that sort of temperature?
No.
Wow. Like best lithium ion I've seen is barely go to minus 20 or sometimes minus 35. But like
say no, even minus 20, the charging is different, discharging is different.
Yes, it does suffer basically loss of performance. Loss of performance.
Loss of performance. In this case, it is absolutely charging and discharging both. Capabilities are available up to as low as minus 60, and we have a patent for that.
Okay.
Granted US patent.
So even if let's say we put this sort of energy storage next to engine, which could get very hot, we do not have to worry about it. We do not have to worry about it. And even in
normally engine temperature will be a bit higher. So if your system permits and the space permit, it is always better to be safe while installing it should be away from the heated area.
No, I'm saying like even if that engine heat, we keep running it and it starts to basically heat up the cabin, I do not have to worry about it, where it's like
worry about it, right?
So you are saying that we can run this sort of energy storage without requiring air conditioning, because many of the new EVs actually have air conditioned circuit trying to cool the cell and maintain the proper temperature. If it's too cold, warm it up so it can actually absorb the energy. If it's too hot, aka India, cool it down so you can gain the energy. And so
say I've seen people using a typical thermal jacketing sort of a thing in the lower temperature.
Yeah, definitely.
To maintain the temperature, and vice versa. If it is hot region, cooling. If it is cold region, heating. That kind of thing is not required for supercapacitor.
Yes. So people who are not aware of it, if you see the teardown of Kia's current electric vehicle where they have blade battery, the battery on top of it, they have a electrical thermal resistor. On top of that, they have an evaporator to make sure that is cooled. So not
Yeah.
only those things consume power, they are also very expensive also to implement. So if we can make sure basically how unfortunately one electric company did try to make lithium ion without any active temperature, it just did not lasted very long. Nissan Leaf. So we can have that sort of scenario, but we do not have to worry about degradation where it's like, okay, it's getting hot, it's getting cold.
Yeah, I see. We are getting electric mobility in slightly wrong mode. Wrong node in the sense, see, because the batteries cannot get charged fast. So we are focusing on range because of the limitation of charging time.
We are power limited, so we are focusing on capacity because we are power limited.
Yeah, now a simple example, even if how many times you must have made your tank full. We don't do that normally in general. Even two-wheeler, the user might put 100 rupees petrol or 200. Why he's not worried about the range in one charge, how much kilometer? He's not worried. You got?
Yeah.
Because there are petrol pumps after every 2 kilometers. But there are no charging stations after, or forget 2 kilometers, even 40, 50 kilometers, like that. Because the charging station in the present timing of charging doesn't make a business model. Neither does the user have that kind of patience and time to wait at the charging station for 4 hours to get the vehicle charged. So if you are able to resolve, or if you are able to match the petrol filling time, range is not the criteria. This hybrid supercapacitors equivalent part, if you are installing it in two-wheeler, it will get charged in 2 minutes. You can charge it in 2 minutes. And in one charge, practical range would be around 70 kilometers, which is same practically when compared to any big brands who are claiming 120. Practically, they are giving 70, 80.
Okay, so let's focus on this thermal part a bit more. What basically, if you drain a lot of current from batteries, they start to heat up. If we put a lot of current into it, it also heats up. So does that same thing happens when you are dumping a lot of current into it in terms of capacitor?
No. See, in battery, there is a BMS which controls the current. You cannot put current. See, remember one thing, when you are charging battery, you are pumping current into that, controlled current. In supercapacitor, it pulls current.
Yeah, that's why it acts as a dead shot if you directly connect a large bank of capacitor. Acts as a dead shot. Okay.
It pulls current. So it is capable of handling that kind of current, whatever it is capable of handling. Like it follows Ohm's law. The pulling is V is equal to IR.
Okay.
So you're not required to control the current while charging supercapacitor. That's level like you are doing in battery.
Although I think it would be more limited by the infrastructure, basically the contacts, the connector, the wire.
See, the charging time of supercapacitor is limited by the power availability from the source. And the other accessories what you have, the current carrying capability of the wire and all those.
So we inherently are not longer limited by the core energy storage, but everything around it. So yeah, so if we can basically, let's just say we have this super duper hypercharger which has giant energy bank that can dump, let's say, hundreds of kilowatts of power in few seconds. The capacitor can easily eat it up. That's not an issue, right? Yeah. Okay. So charging we do not have to, and same rule I think applies in discharging. We do not have to worry about.
Yeah, we don't have to worry about that.
Okay. So right now this sounds like a perfect, but there must be some some compromise. Let's just say compared to normal lithium supercapacitor, what would be the compromise compared to this lithium hybrid supercapacitor?
That is energy density.
Okay.
Lithium-ion capacitor.
Mhm.
You have 3 variant of supercapacitor at present.
Mhm.
One is activated carbon.
Mhm.
The energy density is
Mhm.
6 to 7 watt-hour per kg.
Mhm.
You have lithium-ion capacitor. The energy density is around 23
Mhm.
watt-hour per kg.
Mhm.
You have hybrid version. The
Mhm.
energy density is 65 watt-hour.
Mhm.
The power density part in activated carbon
Mhm.
is around 8 to 10.
Mhm.
In lithium-ion supercapacitor,
Mhm.
it is 8 to 10,
Mhm.
or we can go even higher
Mhm.
in lithium-ion capacity.
Okay.
We have gone up to 15 kilowatt per kg.
15 kilowatt per kg. I mean, like at that point, you are spot welding. I think it is so much
No,
powerful.
no, at 10 only you was spot welding.
Yeah.
At 8 to 10, you are spot welding. We have done that.
Okay.
Then in hybrid supercapacitor, it is 4.5 to 5, or you can take it 4 to 5 kilowatt per kg, depending on the composition percentage. Okay, the self-discharge in lithium-ion is better as compared to activated carbon. In activated carbon, it is around 20% in 1 month. In lithium-ion and hybrid supercapacitor, it is less than 5% in 3 months.
Okay.
In lithium-ion battery, it is around 5 to 8% in 20 days. Or you can take it as 1 month.
Okay.
So there is a
what about the penalty of, let's just say we use that? Would there be any degradation on the material, or like it does not care like what is the C rating or D rating, like in user scenario?
say in user scenario, normally the end of the life is defined. You are referring indirectly to end of life. See, when the internal resistance or ESR of supercapacitor gets double, it is end of life.
Okay.
Yeah, but it is working. But for we define it as end of life.
So
or the drop in value is around 20%. End of life.
So end of life, when we are talking about in terms of supercapacitor, it does not mean we have to throw it away. It's just that it's no longer as healthy as it used to be.
Yeah, it has a, like nowadays in automobile, they are defining second life battery. It is something like.
Okay.
You can use that thing for some other application.
So
normal application.
Yeah, okay. So we have the benefit of basically not to worry about charging, discharging. We have the benefit of not worrying about the temperature envelope. Charging, discharging is not there. Temperature envelope is much more maximized. We do not need to do active temperature control. And we also have to not worry about, practically speaking, about the lifespan, because other components will break down before that. So I think this could, in principle, allow us to go back to the old car system where you used to service the car and it used to keep running forever. So I think we could reach that point where it's like, battery is good. And again, I don't think motor, unless some short circuit happens, motor can also last very long time. I think it's the driver circuitry that is the weak link. So yeah, you can keep servicing the drivers and just like keep running it. So that would be a very good thing, because there is no point of having, energy efficient devices if it keeps breaking itself. The carbon footprint becomes much larger issue, because again, I have a refrigerator, instead of lasting 10 years, it's lasting like 5 years. Now I have to buy 2 refrigerators. What's the point of
recycling?
Yeah.
Recycling.
So, but again, ideally, you should not need to. Like if you have an energy efficient system, and if it does not last long, over time it equalizes. So In terms of lifespan, that's the core aspect, that if it can last as long as a conventional vehicle, we do not have to worry about it.
Your e-waste will go down.
Definitely. That's a critical thing. Okay, what about end of life? Let's just say it happened, end of life happened. Have you tried to recycle it? Like, would it be possible to like extract a useful material out of it?
Yeah. The useful material in activated carbon supercapacitor, you have aluminum on both the sides that can be extracted. Carbon, that way it is not.
Oh yeah, it's okay. Can you guys use copper to improve the current capacity further?
See, copper is not used in activated carbon supercapacitor, but it is definitely used in lithium-ion capacitor.
Okay.
In hybrid supercapacitor and in lithium-ion battery and in lithium-ion supercapacitor, the anode current collector, we call it as a current collector, is copper.
Okay.
Yeah, in the other current collector of cathode in lithium-ion battery or lithium-ion supercapacitor or lithium-ion hybrid supercapacitor, it is aluminum.
Okay.
In normal activated carbon, the anode and the cathode is both aluminum current collector.
Okay. One more question, like whenever we are talking about lithium ion, we also have to worry about the physical dimensions. So generally 18650 is a cylindrical cell. We use cylindrical because it's structurally very sound and the jelly roll is constrained. And when we are making prismatic cells, we have to constrain it, like physically clamp it so it does not expand and contract and self-destruct. So is there any limitation like that in your chemistry?
See, there are basically 3 form factors by way of which you can make battery and supercapacitor. 3 form factors. One is cylindrical. What we have referred is 18650 or some other diameter. 18650 is actually a diameter. 18 mm is the diameter of that, and 65 is the height, mm. Similarly, you have prismatic,
this cell,
wherein
18650.
Yeah, you have prismatic, wherein the winding is done, but it is oblong. The idea is to gain, because in cylindrical, what happens? There is lot of space wastage when you make a module out of it. The round the internal, the side part, it gets wasted.
Packing efficiency is poor. You can't pack it tight enough.
Poor, tight. So to overcome that, people came out with the prismatic, like winding round but loose and pressed, so it becomes a square sort of. But in that, there is a lot of stress on the corner part, on the side where the lower electrode is having lot of pressure from the upper one.
Okay.
Yeah, these are 2 form factor. The third form factor is stacking, wherein what you do, you take anodes separately, put a separator, put a cathode, like a cut pieces, one above the another.
So a sort of Z folding like this, you are talking about, like Z folding?
No, but the refolding is done only for separator.
Okay.
But the electrodes are totally
continuous.
Not continuous, separate. Separator is continuous.
Okay.
Separator is continuous. The electrodes are cut pieces, kept one above the another. This gives you a perfect geometry, because it can be every inch of the square can be utilized. Secondly, because they are separate and we are at the end connecting them together, there is a better equivalent series resistance.
So you're sort of parallelizing all of them,
parallelizing all.
So it's like this, parallelizing like this.
Round what happens? The point of injection of current or point of deriving current is one particular spot, or it may be 2. But in this case, every layer is that spot. So the current distribution is very uniform. Because of that, the I square R,
Mhm.
the heat generation
Mm.
formula is I square R,
Mm.
where I square is the current, R is the resistance.
Mm.
Your resistance goes down in stacking,
Mm.
so your temperature goes down.
Okay.
The particular, so there is a even distribution of temperature,
Mhm.
and because of that, you can take a liberty
Mm.
of making what you call it as a packaging material more cheaper.
Okay. So it does not need to be aluminum cans, which we generally utilize for prismatic cell. It could
Correct.
even be a plastic can if we want to.
Plastic.
Uh,
Normally, it is a resin filled plastic,
mhm.
which is used for that.
Okay.
It is known as pouch cell
Mhm.
or a laminate cell.
Okay. But it does not
So,
require compression from side to side, like prismatic lithium cells that require.
no, it requires compression only at the time of manufacture.
Okay. But not in use, basically, once we are, because. Okay.
Not in use.
Okay. But if it can be packed efficiently, the packaging efficiency can become a really
Yeah.
useful.
See, because as it is exactly square, you can get a better volumetric energy density also, watt hour per liter, apart from watt hour per kg.
Yeah, because on paper, even if you compare it to lithium ion right now, on paper we should be here, but we rarely get above here simply because we can't
See,
pack it.
On paper, what we do, we refer the energy density of a single cell. But while using, we are making a power pack. So the effective energy density should be a complete power pack, volumetric and by weight.
Yeah, but at that point, it's no longer as great as we think. It's basically the packaging efficiency is not there yet. People are trying different. I think the best I've seen is BYD's blade packaging, because again, on packaging term, it does improve.
Yeah, that is the laminate cell.
Yeah.
That is stacking.
So
not prismatic, neither cylindrical.
But again, that was the critical point. The best design aspect of it was that BMS was on the side. They did not need complex wiring. It was just directly tapped on, and cooling and heating was also done very easily from side to side. I was still confused why they did not have resistor elements bottom and evaporator on top. They had both on the same side. When they did the tear down, it was confusing to me. It's like, shouldn't you put resistor on the bottom? It's like, but again, they must have made sense. I think it's manufacturing wise, it makes sense. So how much can you what is the current condition when it comes to manufacturing it in large scale? Let's say 100,000 units of it you have to make. Where are we at that point in time?
See, basically, we are in the mode of expansion. This is a hardcore technology. The machines not available off the shelf. So it is a evolution process. Right now we have a capacity of 10 megawatt annual.
But you have solved the issue of manufacturing, right? It's just the scale, as in like you have to buy bigger
scaling
tools.
Up. Yeah, it is just a see, we have completely solved the manufacturing issues. There is no bottleneck. In between we were synchronizing the thing, because we have a coater. It is a big setup. Coating machines are there, stacking machines are there, winding machines are there. Every machine has its own capacity. So first synchronize the thing with the existing, then replicate it.
Okay. So you are making sure that you do not create a scenario where you are bottlenecked by one machine, or it's like it's better everything is running in synchronous mode. It's like all okay.
And once that is done, then you have to scale it up. So the first part will take longer time. The adding up the capacity, the time gap will be reduced.
Okay. So have you used this technology in any real world application?
Yeah.
Example?
See, we have given a supercapacitor for artillery gun. We have vendor to ISRO. Yeah, and we have given a practical demonstration of electric Tata Safari.
Running on this hybrid lithium hybrid capacitor.
No, running on external hybrid.
Okay.
It was in 2019,
Okay.
wherein I told you, you take batteries separately,
Uh-huh.
supercapacitors separately,
Mm-hmm.
put them together
Mm-hmm.
and use it.
Okay.
So that was the first step for hybridization
Mm-hmm.
in 2019.
Mm-hmm.
Now
So-
we are in 25.
Okay,
So it
so
took,
yeah, that's a lot of. So what else you are working on? So this is the core technology. You have solved it, and you have explained all my doubts. So I'm very happy about that. So what else you are working on right now?
see, as I told you, batteries and supercapacitors are converging technology.
Mm-hmm.
We have developed solid electrolyte,
Mm-hmm.
which will resolve, like I told you, the electrolyte in the present lithium battery
Mm.
is volatile
Mm.
and flammable.
Mm-hmm.
So this solid electrolyte is not volatile.
Okay. Okay. There is a bit of confusion for me. When you say solid, what do you mean as in solid? Because again, the battery itself is solid. So are you talking about the liquid that goes into as a electrolyte or?
Yeah, I am talking about the liquid.
Okay.
Because battery in battery, your anode cathode separator is solid.
Uh-huh.
Okay.
Uh-huh.
Only the electrolyte is liquid.
Uh-huh.
In the lithium battery, mobile battery,
Mm-hmm.
it is a gel,
Mm-hmm.
polymerized
Mm-hmm.
sort of.
Mm.
So we have developed a solid electrolyte.
Okay.
It is not gel,
Mm.
it is not liquid, it is solid. Now, the beauty of that, imagine, actually, you must have seen a 12-volt battery,
Mm-hmm.
let us say,
Mm-hmm.
single battery, 12 volt. It is having 6 point of where you are putting water into that.
Mm-hmm.
All these 6 compartments are separate.
Mm-hmm.
So basically, your 12-volt battery comprises of 6 cells
Yes.
put together,
Mm-hmm.
but they are completely isolated
Yeah.
at the basic level.
Mm-hmm.
Electrolyte from this cannot enter over there because it should not.
Mm.
Okay.
Mm.
But in case of solid state battery, you don't have to put any partition in between.
Okay. Okay, so
So
then how we'll have galvanic isolation?
say you can always use an insulation
Uh-huh.
in between.
Okay.
Like you are already doing it in normal part. In your 18650,
Uh-huh.
the upper sleeve portion, which is blue in color
Uh-huh.
or whatever color, that is insulating material.
Okay. So you do not need structural, what we call
Correct.
structural
Yeah.
material requirement goes away. So basically, you can make sure that it is a very.
So you can
use the plastic part itself to basically isolate galvanically. Basically.
Galvanically.
Yeah.
You can house the complete cell, stacked cell, in a single container.
Oh, okay.
So you will be saving on space, saving on cost of packaging material. So the energy density goes up. And what we have noticed, as per our trial, it goes up by 4 times.
Oh. Okay.
Panel pack level.
Okay. Yeah,
pack level.
Not
cell level, pack level.
Pack level matters because on paper, cell wise, which should have been like 1,000 kilometer range should have been done long ago. Okay, one thing I want to understand. So whenever we talk about normal battery, so the idea is you have anode and cathode. You coat material on them. You put separator. You create the jerry roll. Put it into a container. Inject the what we call electrolytes. Yeah, and so how would you construct it when it's solid? What's the layer stack up?
Say you take anode, cathode, and you don't require separator.
Okay. Wait, really?
Yeah, because the use of separator is to electronically isolate anode and cathode. Okay, that is one use. Second, when doing electronic isolation, it should allow flow of ions. That is done by electrolyte because it is solid. There is no electrical short. It is isolated.
Okay.
It is a physical material which
Still,
acts like an insulator.
okay. But still allows ion flow to happen without.
Yeah, the purpose of electrolyte is flow of ion.
Okay.
It,
Okay. What does it affect, like in terms of dendrite formation that happens when you charge and discharge the lithium chemistry?
yeah, dendrite formation is altogether different part, wherein the separator gets punctured. Okay, it gets punctured. How it gets punctured? Because by over a period of charging, like in general, you must have noticed when a liquid is flowing on certain material, or it might develop humps.
Surface tension. Okay.
Surface. Those are dendrite in that battery. There is some deposition of lithium. Layer goes adding up at certain point, and finally it punches the
separator.
And your anode and cathode are coming in front of each other, electrically shorted.
Okay. So if you are using solid separator, basically, would that make a dendrite formation less of a problem? Can it tolerate?
No, dendrite formation will be there, but safety part will go up.
Okay, so you can tolerate far more dendrite. Okay. So,
but again, you know, here we are referring this like we are using the same anode, we are using the same cathode. Okay, but in solid state battery, that is not expected. You have made solid electrolyte, that improvement is there. Now you have to improve the anode also.
Okay.
The anode thickness required is more to accommodate this thing. And basically, solid state battery at the fundamental level, it is just electrolyte liquid replaced with solid electrolyte at fundamental.
So it's pulling double duty. It's acting as an insulator also, separator, and also as an ion conduction medium.
Yeah, but it is this basic work.
Yeah.
The conduction, see, separator needs to allow conduction of ion. And the conduction of ion is done by electrolyte. इधर अलाउ करने का सवाल ही नहीं उठता ना, because so at technology level, production and manufacturing level, there are many other changes at the anode and at the cathode in the solid state battery, and also there are many changes in the pre-lithiation part to accommodate all those things.
Okay, what sort of lifespan we are looking at? Does the cycle count goes up? Let's say normal lithium
ion is 2000. Cycle count, it goes up to 8 to 10,000. Means comparatively, lithium iron phosphate, which is showing 2000 cycle, the same battery with solid electrolyte, and of course that manufacturing process will give you a life of 10,000 cycle, 8 to 10,000 cycle.
Okay.
The C rating also goes
up. Why? But you are increasing the physical separation distance, so why C rating is going up?
See, what is C rating? It is the capability of handling the electric current without getting ionized.
Breakdown, right? A sort of breakdown. Okay.
Sort of breakdown. Because the other technological parts are going into the anode part, the anode is much improved anode. And liquid is not there. Normally, there is a deterioration of any material bonding in presence of liquid. So that is avoided.
Okay. So yeah, that's a very significant improvement. And then again, what about the voltage? Does it remain exactly, the voltage curve remains exactly like a normal?
Yeah, the voltage remains the same, but due to one typical process what we follow, we can increase the voltage by 0.2 to 0.3 volt over the existing one.
Okay. So is it just at the top of full charge voltage of 4.2 goes up, or the what you call nominal voltage? Which goes up?
Nominal voltage, working voltage.
Working voltage goes up.
Like for example, I will tell you, we have a advanced lithium battery version of lithium iron phosphate, wherein normal lithium ion battery, lithium iron phosphate, the nominal voltage, the operating voltage is 3.2. With our typical process, our nominal voltage is 3.3 to 3.4.
So at large enough pack, it will improve the energy density also. If you
Yeah.
have like a 50, 60.
Yeah, the energy density has gone up in solid state battery by 4 times. So if you any car giving you a mileage of in one charge 400 kilometer with the same weight of the battery, you can multiply it by 4. 1600.
And what about its temperature systems?
That has also been already improved.
Okay. So does it match a capacitor?
Even the safety portion is improved.
Okay.
It is, I told you, no, it is converging technology. They are moving more closer towards that.
Okay. So inherently they are started as two separate things. They are slowly merging together, where they are becoming just one.
Converging together.
Okay. So, wow, this was a very in-depth interview. I'm very pleased with this. Thank you so much for your time. Would you like to give some closing remark?
You are doing a great job.
Thank you so much. So, as you guys see, this was our interview with the great, let's just say, energy storage guru.
My sentence was incomplete. You are doing a great job. Not by taking my interview, by supporting technology. Various technology, I have seen you covering a lot of topics on technology, creating awareness. Keep it up.
I'll do my best. So thank you guys. I hope you guys have enjoyed this very in-depth and very top-level interview that we did. And I hope to see you soon in our next interview. Bye.
Thank you so much. Thank you so much.